This panel we're going to talk about the latest processes and technologies in aerospace programs and why these partnerships are so important. We have Jacomo Corbo from PhysicsX and Massimo Maroni from Leonardo, and this panel is moderated by John Thornhill from the Financial Times. Give them a round of applause and bring them on stage.
Well, good afternoon. Great pleasure to be here this afternoon. And our topic for discussion is software-defined hardware, the next industrial revolution. And we were hearing earlier this morning how we were told software is a solved problem. More or less, we know how to build and develop it and deploy it. But software-defined hardware is an unsolved problem. Well, in the next 20 minutes, we're going to solve it with the help of our two panelists. One from one of Europe's best-known established primes, and one from one of Europe's most interesting startups. So Massimo, who's from Leonardo, can I start with you? Your company spans all kinds of activities, from manufacturing aeroplanes and helicopters to cyber and satellite services. Mark Andreessen, a few years ago, famously said that software is eating the world. To what extent is software eating the defense industry?
Yeah. Good afternoon, everybody. It's a pleasure to be here. Yeah, software is really shaping a new world for defense in two main aspects. First of all, we have the software that is embedded on our products. So, of course, software is more and more important in the product. So we need software within the equipment. We need very flexible software that is easy to be updated. But not less important, we need the software in the development chain. I mean, the development chain, so all the activity that the engineers do to develop a product use software tools. I mean, we often forgot that the development is really based on software. So we have model-based system engineering, we have model-based design. So it's a very important part of how an aircraft is built. And during this session, the work that we have done with Giacomo is mainly on this second part. We've heard this morning on the MIT intervention, Fiona and Klaus, that we need to speed up the time for development. There was a slide on the Eurofighter that said plus 5 years. I would say that that was optimistic. If I took the development time for the Eurofighter, I think it was double. And we can't afford anymore that. And in order to shorten the development time, we need better tool, we need faster tool. And it is really important that the tool chain for development becomes faster and faster. This means two different branches. One, for sure, we need to work on hardware. The GPU revolution is already there. We need to develop software that is suitable to exploit the GPU revolution on one side. On the other side, we need smarter software. What we have done with PhysicsX is to take a standard development tool to do computational flight dynamics simulation that is one of the most expensive, time-expensive activity during the development, and try to see how to shorten 10x the time needed to do this simulation. This would allow to explore much more alternatives during the design phase. So this is really a big point. Not just to reduce the the time, but also to explore much more alternatives to find the best one to meet all the requirements.
Can you go into a bit more detail? What specific kind of services, systems are you developing that you can now accelerate that development time?
Yeah, let's say that in the first phase of the arc, now we are talking about a new program that, broadly speaking, is within the GCAP program, the tri-national program. And we are talking about the really first phase of development when we are focusing on evaluating different alternatives. In order to do that, you need to define the aircraft shape and to do a lot of simulation along with wind tunnel test to understand if that shape is meeting the requirement. And this is done with these CFD tools that takes days, week to run. What we have done with Giacomo is to build a different way to approaching that. So run a small set of this simulation, and based on this small set, to build a much faster model based on deep learning surrogate, so that we can use this surrogate model to do the preliminary phase of the design. And this allows really to shorten the time.
Great. Giacomo, not everyone in this room, I think, will probably know about PhysicsX. You're a very new company. Can you tell us what you do and how you've ended up working with Leonardo?
Not yet, exactly. We're building a new engineering simulation software stack. So the whole idea, I think, is to enable much more software-defined hardware innovation. We're starting from the premise that a lot of what stands in the way of automation and optimization in engineering or in manufacturing is really what the compute around simulation looks like. It's numerical simulation. It's very compute intensive. It takes a lot of time. A lot of how engineers spend their time is around manipulating meshes. It's a lot of the pre-processing of those meshes. It's post-processing of it. It also means that a lot of that runs through engineers who understand the physics incredibly deeply, or understand the applications very deeply. And so in moving that to inference, to having AI models that are very good at predicting the physics, that are trained on a large corpus of data, which is tied to numerical simulation for the most part, we're in a world where that is accelerated pretty substantially. So not 20-30%, but by anywhere between 10 to the 4 and 10 to the 6. So for things like CFD, more on 10 to 50,000 times. For things like computational electromagnetic field simulation, closer to 800,000 times faster. So we're building what we think is a very different software stack to change how simulation is done, that now handles simulation data at scale to be able to train these models. And these are models that, one of the things that's, powered a little bit the AI revolution when it comes to large language models, to multimodal foundation models, to everything that's happening in robotics as well, is scaling laws. And one of the things that we see in our domain as well is that these are data-driven models, these are data-agnostic architectures, and we are seeing scaling laws hold here as well. And so the degree to which they offset numerical simulation grows super linearly in the size of these models. And maybe one of the other things to highlight is that, look, in so many hard engineering contexts, the simulation itself is a proxy for what happens in the real world. And so, if you're building a jet engine, for example, you'll simulate how an airfoil on that jet engine behaves, in silico using your numerical simulation tools. And then after that, you'll build that airfoil and you'll trial it in a wind tunnel for 50,000 hours plus. And the reason for that is there are all sorts of hard effects, hard to simulate effects numerically, things like flutter, And that's why we build the physical things, and that's why there's so much physical testing that is, and this is true in semiconductors, it's true in a lot of different domains. But one of the things that we can do when you move things to inference is that you can also train directly on experimental data. So whether that's some test bench, a wind tunnel, a wet lab, we can fine-tune these models on experimental data so that the models themselves are not just a whole lot faster, they're also more accurate insofar as they're able to pick up a lot of these, these complexities, these instabilities that are part of real-world engineering and manufacturing.
Mm-hmm. And you work across a lot of different sectors at PhysicsX. How do you find the defense sector? Are they particularly receptive to this new way of working, or are they actually quite resistant?
So I think they're incredibly receptive to it. Aerospace is our largest sector, or aerospace and defense. And then after that, it's semiconductors. We also do work in materials processing. So think of commodities like copper or lithium, or scandium alloy production, steel, and then automotive. And I think there are two things here that mean that aerospace and defense is receptive to onboarding new technology. Like one, I think, is just a recognition that the complexity of the products that they're developing, whether these are next generation airframes or jet engines, are of a complexity that numerical simulation is absolutely a bottleneck, right? If you're trying to simulate, and this is in the public domain, like the combustion cycle in the first two stages of the largest jet engine that GE makes, the GE9X engine, a single simulation will take you about 500 hours to run, right? And so the kinds of design of experiments, the ability of engineers to be able to search a space, as Massimo was saying, is incredibly constrained. And so I think, one, there's just a recognition that these organizations have to find an alternative to today's engineering tools and to what they're currently, for the most part, operating on. And the other one is, what Massimo was calling out, which is the real imperative from a speed and acceleration perspective. So, the GCAP program will have to be delivered much more quickly than the last Eurofighter program.
Mm-hmm. Okay. And we were also hearing this morning that some investors are still quite reluctant to invest in the defense sector. You raised $135 million, I think, this summer. Did you find investors were reluctant when they knew that defense was one of your areas of investment?
So we are very much dual use. We're operating against, in different sectors, but it was very much, a question that we posed to whoever we were speaking with, which is, we didn't want to have any impediment on being able to go after the sectors that we wanted to be relevant to. And certainly, aerospace and defense are joined at the hip in a very, very fundamental way. I would say that, maybe that, might have been an issue a few years ago, but even our lead in our Series B, so, General Catalyst led our Series A. General Catalyst has been in the space for some time, let's say with their first investment in the space, it being in Anduril, in the defense tech space specifically. Atomico and Temasek, led our B. And, Atomico in particular in Europe, does not have a long track record of investing in defense tech or even in dual use technologies. But they were very happy to come to the table, and they didn't have any limitations. Mm-hmm. Yeah.
Okay. Massimo, one of the other things that we were talking about this morning was that you have to have a lot of trust to operate in this sector. Traditionally, I think a lot of the primes have found it quite difficult to work with startups. These are new companies. They don't have a proven record. So what do you think are the most important factors in building that relationship of trust with startups who you want to partner with, particularly when it comes to issues like kind of confidentiality, security, and so on?
Yes. Yeah, this is an important issue. I think that I can talk about the experience and the trust relationship that we have installed with PhysicsX. So we started really working together on the same site with a group of engineers coming from PhysicsX, and we really appreciated the technical competence and the, I would say, the ability of transferring this competence and this methodology. Of course, we, as Leonardo, had a lot of competence in the specific design product, but for instance, we don't have a lot of competence in the artificial intelligence, in the neural network part. So one of the goals since the beginning was to merge these two competences without any barrier. So openness on PhysicsX side to transfer these skills to our engineers, and openness on our side to help on the technical. And I think this worked well, also because there was a joint team resident in Turin, in Italy, doing this work. And another thing that I really appreciated is the vertical competence. So as Giacomo was saying, they put on the team people that had physics skills, artificial intelligence, machine learning, so they were able to deal with the whole project from the beginning to the end. Coming back to the security part, because I think this is important. We have, as a defense industry, strict security policy. So we have programs that are not classified. We have programs that are military classified. So I think a good